Okay, everybody. Um, just recorded an hour of this and I get this weird screen, so you guys don't see this. But we're going to continue our discussion of the angular momentum operator and what you're going to do in the second part of your final exam is you're going to be deriving an equation in terms of quantum mechanics for the angular momentum operator. But before we do all that, I want to start off our discussion with what we understand about angular momentum. Say we have a bird's eye view here of a particle spinning around a circle, a radius r, and we understand that angular momentum is going to be equal to mv times r, which is also equal to I omega, where omega is the angular velocity. So this particle spinning around, and we know it has linear momentum of mv. We know that in this scenario that angular momentum is a cross product of the radius and the linear momentum. So if you use your right hand and symbolize your thumb as the radius, and your hand is going to be in the plane of the page, right? So your thumb is the radius and your fingers represent the velocity. Your palm represents the angular momentum vector, and your palm faces out of the page. That's why the angular momentum will be out of the page, indicated here. And then the angular momentum vector and all the angular quantities are about the circle. We are going to be transforming from our regular coordinate system, x, y, z, into the spherical coordinate system of r, theta, and phi. The reason being because we're treating the electron like a sphere and it's rotating. It has angular momentum, it has spin angular momentum, it has orbital angular momentum, it has total angular momentum, all these quantum values or these operators that produce quantum eigenvalues. Such as the nature of quantum mechanics. Really cool stuff. And I hope you guys, take it in college and develop an appreciation for it. And then you can get an understanding of what this quantum computing thing is all about. Because all it really is, in my humble opinion, is a way of normalizing wave functions in order to produce these qubits. But doing that is an engineering problem. The physicist has already stated, hey, this is you got to do it this way, and maybe they're having some more success now or whatever, but that's an engineering problem now. So, I think I was watching this Einstein video, and one quote was, "Where would the engineers be without the steadying hand of the physicist?" And that's right. So, we proved it. We got the theory. We got some instances of it. Now you got to go engineer it and mass produce it. Okay, so we're going to be talking about the angular momentum vector. We know it's r cross p, which is a radius cross the linear momentum. And linear momentum is mv cross r, which is also equal to I omega. Now, there's two types of products, the multiplications. There's the dot product, and then there's the cross product. The dot product is going to give you a number all the time. So when you have two vectors along the same axis, whether they're parallel or anti-parallel, 0 degrees or 180 degrees, you're going to get a scalar. And for the cross product, you have those two vectors that cross to produce a new vector. So there's still multiplications, but there's two different types of multiplication. And since we're dealing with an angular momentum vector, which is the cross product of radius and linear momentum, we have to treat it in the right mathematical way in order to produce the angular momentum values along the x-axis, the y-axis, and the z-axis. So basically, we're going to use something called cross product math in order to produce L, because we've been taking it for granted. Okay, get a mass, get a velocity, get a radius, we have angular momentum. Yeah, true. And we know right-hand rule is going to be pointed out. But mathematically, there is a more exact way of handling the cross product of two vectors. So like I said here, force and radius are perpendicular. We have a torque that's going to be out of the page for this configuration. So the dot product, what the dot product does is it produces scalars always. Two vectors dotted together give you a scalar. And two vectors crossed together will always give you a new vector. We didn't have magnetic fields in this class, but when you cross a velocity vector and a magnetic field vector, you are always going to get a force, a magnetic force. So the magnetic force is always going to be perpendicular to the plane of the moving particle. That's why in, let's say you have a wire with current running north, and then you have a magnetic field that's running into the page, for example, the magnetic force is going to be going to the left. It's going to bend the wire to the left. So what that looks like is like, say for instance, you have a magnetic field that's represented by these X's and like a box. And then you have a wire of current I going up. And so that's a series of, say, protons moving up through the wire. So you can call them all with speed v. They have a collective b to them, right? They're all basically b, for the sake of argument. But I guess, you know, on a lower level, or I guess a statistical level, that they're not all going to move at the same velocity, but the electric field is going to be constant. So blah, 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 blah. The velocity moves up, the magnetic field moves in, and the magnetic force will be, yeah. I don't know why I get these boxes. Not a smart guru. Okay, the magnetic force, goodness, what is happening? The magnetic force will move to the left, so F. So the wire will bend left in this configuration. And if the magnetic field was coming out of the page, then if the magnetic force was coming out of the page, then, or the magnetic field was coming out of the page, then the force would be going to the right. So it's all right-hand rule stuff. Anyway, that's just an illustration to show you that the cross product is always going to give you a new vector. Okay, back to the dot product and all that stuff. So dot product, you have to have both vectors in the same axis. When you have, and we know that the x-axis is represented by the I hat unit vector. So this is two products, two vectors along the x-axis to produce a scalar. And then this will be two vectors along the y-axis to produce a vector, a scalar. And then this is two vectors along the z-axis to produce a scalar. So dot products are always going to give you scalar values or numbers. Energy is just a number. Now, cross product, you have two vectors crossing to give a new vector. So like you have two vectors that are orthogonal or perpendicular to each other, like the x-axis vector and the y-axis vector gives you z. I cross j gives you k. J cross k gives you I. And k cross I gives you j. So basically, the vectors that are crossing produce the vector, the one that's hanging out, right? This is x to y gives you z, y to z gives you x, and z to x gives you y. You know, so it's always the one that's missing. So you can't have a cross product along the same axis because they're not perpendicular. They are parallel to each other. And likewise with the dot product, you can't get a dot product of two vectors, two different vectors, because they're perpendicular. So the dot product deals with parallel stuff and cross product with perpendicular stuff. It's perpendicular values, okay? It gives you some kind of appreciation too with normalization. So when you normalize eigenfunctions, what's happening there is that you're normalizing two you're normalizing the opposite of the eigenfunction with itself. You're basically saying, say I want to multiply e to the ix with e to the negative ix. Well, both of those eigenfunctions must be along the same axis, and that's the only way that you're going to get a value out of it. You're basically doing a dot product in a fancy schmancy way. You got an integral of opposite complex conjugate, but it's a fancy way of doing a dot product. And what I have here is an illustration of dot products that the values along all of the axes in, say, a 3x3 matrix here. So let's say I have a 3x3 matrix, and I have three values along the x, three values along y, and three values along z. The only values that make sense for normalization are the values along, or when both of those wave functions are in the same axis. So the xx values, the yy values, and the zz values are the only ones that matter. So this is what is known as diagonalization of a matrix. And when you diagonalize a matrix, basically you're saying the only values that matter are the only values that really exist in when you normalize a wave function is the values that are along the axes themselves. So again, if you have a wave function e to the ikx and you normalize it with its opposite, e to the negative ikx, okay, cannot be e to iky. It has to be the opposite one along the x-axis. When you do that, you're going to get an xx value. You're going to get a scalar. You're going to get a number. Something's coming out, a qubit, you know. And so thing with yy and same thing with yz. The ones that are off axis, they're there, but in terms of once we get the values along the diagonal, those parts of the wave function collapse pretty much. And that's what is known as the collapsing of the wave function. You only are going to observe the normalized wave function themselves. The other ones off axes, they're not normalizable, AKA you can't see them. Possible, but you can't see them. So that's just a further appreciation of this dot product business. Okay, back to the cross product, because we're dealing with angular momentum, which is a cross product of radius and linear momentum. Wow, I did a whole hour of this, and you can only see like some weird screen of like, oh man. And I knew when I initiated this Zoom, something funky was about it, because I didn't see my normal screen where it showed the smart board, but I was like, okay, it's there at the top, so must work. An hour and 3 minutes down the drain. So maybe this one will be shorter. Okay, so we have angular momentum equals radius cross with linear momentum, and we're now going to treat it in a full exact mathematical way to get an appreciation of what the cross product actually is. The angular momentum can be made up of three components, x, y, and z. That means you can have spin about each axis if you want. So the full angular momentum is made up of three components, Lx, Ly, and Lz. And Lz is going to be the most important one for us today. And it's the most familiar because normally we can visualize things spinning about the z-axis. It's like a spinning top, right? And the x and y's are just spinning up, rotating about z as the top spins on the table, like in Inception. Okay. Let us now examine the cross product. So we have three components along their unit vector axes, x, y, and z. So we have I hat, we have j hat, and we have k hat. So we know that the axes corresponding to I hat is x, and then j hat is y, and k hat is z. So those are the axes to the unit vectors. And or we can say Rx, Ry, and Rz because it's this sphere, this electron can spin about either one of those. But I just do X, Y, and Z just to make the symbology a little clearer. And then we also know that the momentum can exist along each axis, px, py, and pz. So this is basically your r, and these are your p values, right? And we're going to cross them together. When we do a cross product, we're going to hold one of the axes fixed and cross the other two, just like we did above when I crossed J and K to produce I. And that's exactly what I'm going to do here for the first part. So when I do a cross product with the unit vector I, I'm going to cross J and K, and then I'm going to subtract and produce K and cross K and J. That's just the mathy way of doing a cross product. We don't have to go into the details of why that is. We're going to use it for sake of argument. Okay, so J to Z, or J to K, which is YPZ minus ZPY. That's what we get there. And that's going to be our angular momentum vector along the x-axis, LX. It's basically the stuff in the parentheses is LX. And we say along the I hat, just like you say, okay, well, force, back in APC Physics 1, that's going to be 4I hat. So we know that that's going to be, 4 newtons along the x-axis, to indicate that this is a vector, right? Scalar, number, and direction. Or negative 4I hat, positive 4 newtons. So that same thing, right? So that's what's going on there. So LXI hat. So LX in the parentheses. And the same thing for the cross product of LY. So when we do cross product LY, it's going to be minus J hat. We're going to hold the J hat column fixed, and we're going to cross I to K. So we're going to do XPZ minus ZPX. See, XPZ minus ZPX. And that gives me my LY. And then likewise for LZ, this is one of the most interest for us. We're going to do plus K hat, and we're going to hold the K hat column fixed. Use my mouse, I guess. So hold the K hat column fixed, and we're going to do XPY, YPX. So we have XPY minus YPX. Now, if I had 10 of these unit vectors, I just alternate minus, plus, minus, plus. That's just the nature of this cross product business. For positive, negative, positive, negative. Again, that's math, and we're going to extract some physics out of it. So we do the math operation so we can get correct physics, right? So LZ equals to XPY minus YPZ. Okay, so like I said, all the stuff in the parentheses is the stuff that matters. So LX is equal to YPZ minus ZPY. Again, if I have values for these, I get a number with a direction, the I hat direction. And then LY would be XPZ minus ZPX. So technically, this is the scalar of angular momentum. Then LZ would be XPY minus YPX. So again, linear momentum is there. That's classical physics. In quantum mechanics, we won't derive this, but in quantum mechanics, momentum is negative IH bar del operator. Okay, you just take it for granted for now. The derivation of that is a little above your pay grade only for right now. You're going to get there, and this is going to be quite simple. But again, P negative IH bar. This all, this H business, when you see H's all over the place, you're dealing with quantum stuff. You're dealing with Planck's constant. You're dealing with very small particles. But H bar, just to remind you, it's H over 2 pi. Where H is the Planck's constant, right? Not the Planck's limit. The Planck's limit is 10 to the minus 34 meters. That's as small as you can get. Before what happens? Singularity, infinities. Who knows? But that's so-called the smallest number you can get. But the Planck's constant is just it's a joule second. It's basically the constant that deals with small particles that have particular wave-like properties. It's the small Planck's constant. So when you see those H's, you're in quantum. Okay, so like I said, the del operator is a full partial derivative. It's a partial derivative along all of the axes, all three axes. So we have a partial derivative. The del operator is, by definition, a partial derivative of del x plus del y plus del z. If this was like del x, you'd just be dealing with the first one, del y, and del z. But since it's written that way, then that means that you have this momentum that can exist partially or full, but in partial form over these three axes. So again, this is the quantum mechanical description of momentum. Here's our momentum description that we know. Therefore, I transform px into negative IH bar del x, borrowing from here, and which is just going to be negative IH bar del x, right? And this is the full. And then py is equal to negative IH bar del y, and pz is equal to negative IH bar del z. Okay, so we have all of those guys. So again, this is just going to be negative IH bar y, IH bar del z. So we have Lx equals negative IH bar y, I said pz, right? Or py. Well, py is equal to del y. Not, well, Lx is negative IH bar y del z, which is y pz. Pz is equal to IH bar del z. That's why I have that here. Negative IH bar del z for y pz. So negative IH bar y del z minus z del y. So all I'm doing is I'm transforming the Lx operators, Ly operators, and Lz operator in terms of its quantum mechanical form. Because we need to deal with that in terms of our electron later on down the line when we get into the spherical coordinate nature of the electron. Or better yet, just simpler than that, we're dealing with, since we have to transform the momentum in terms of its quantum mechanical form, because the electron is a very small particle, and so we have to talk about its momentum in terms of its quantum mechanical form. So not just your pz and your py and your pz, your px and your py and your px's. We have to transform them into the quantum mechanical equivalent. So what I have here in the box is the most important operator, vector, that we're going to be deriving in terms of spherical coordinates, which I want to talk about next. And we will then be using the spherical coordinate nature of Lz to get a more simplified form of the Lz operator. The Lz operator upon the eigenfunction that relates to the angular momentum is going to produce particular discrete angular momentum values. And so what we need to do before that is we're going to get a full eigenvalue equation for LZ, for the angular momentum along the z-axis. And that's very similar to what we derived in the previous video, where I had h side equals e side. That's a full eigenvalue equation. So we're going to get an equivalent one for the angular momentum along the z-axis. And then what we're not going to do is describe the discrete angular momenta along the z-axis, because there are particular subsets of angular momentum that can exist, the possibilities for angular momenta, instead of just one value. That's a deal in quantum mechanics. We can get a large series of values. And that also reminds me, this is why a lot of times on that level, you're going to be seeing solutions in terms of like a power series. When you get power series solutions, I like to think of those as your different possibilities. Now, the power solutions, power series solutions are going to, for the most part, after say the second order or the second value in the power series, they're going to start to get so small or so negligible that you really don't have to express those following values. But you're going to get power series solutions on the next level in college to a certain point. So those are basically your different possibilities that you can have for something like, say, angular momentum. But again, power series, if you haven't seen it, you'll see it in calculus or you see it in one of your math classes. But yeah, the thing in physics is you're always going to be using the math that makes the most sense. You're not going to use every bit of math that you learn, just ones that fit the physics that's actually going on. You're going to see a lot of power series, maybe Taylor series, when you're dealing with, derivatives. Taylor series is basically a series of derivatives for a particular function. Power series is just like a series of possible solutions. Binomial series, you see that. So, those three will be well in hand at some point in your future physics environment if you take physics on and on. Yeah, so like this eigenvalue equation here, we can get different energy values. It's not just going to be 2 joules. We can get all kinds of energies based on this wave function, because this wave function dictates everything. That holds the key, for all the energy values. Now, this operator here is just one particular value, one particular thing. The eigenvalues are dictated basically by the wave function, because you can get a series of those. These operators are very distinct, but you need them in order to get the eigenvalues. So they all work together. You cannot have one without the other and all that stuff, as I displayed in the previous video. Okay, so next, we're going to be talking about the electrons. So we're going to be breaking up our 3 dimensions of X, Y, and Z into spherical polar coordinates. Spherical coordinates for short, but I'll just write up here, spherical polar coordinates. Now we know what polar coordinates are. It's just r and theta. So we have a circle, and a circle has a radius and it has an angle going all the way around. Well, spherical polar coordinates is we have we have another variable. We have the phi vector. So we're no longer just dealing with a circle as in this plane here. So we have, hopefully you can see my little cursor, but this little green line, that would be my radius in a circle, and I have my angle theta. Or you can just look it up here. So I have let's say I have a circle in the plane of the page. Okay. R and theta, that's polar coordinates. Well, then spherical coordinates involves yet another vector we call phi. So let me explain them in easier detail. Okay. you have a sphere, you have a basketball, or an electron, or a proton, or a neutron, anything that's spherical symmetry. Sphere has a radius r along this line here. It has angle theta. This theta angle is the precession angle. That means it's wobbling about, as it's spinning around, it's wobbling. So the wobble angle, if you will, is your theta. And the rotation angle is your phi. So it just spins around, in this case, counterclockwise, 0 to 360. And the precession, normally the precession is going to go from 0 to pi. That means you can have it spinning up and spinning down, which introduces actually another quantum operator called spin. Probably have heard of it in passing, but there's another quantum mechanical operator called spin, which is a little bit more esoteric to deal with, insofar that it deals with half integer values. That's pretty much the only one that deals with half integer values. There's one other, I believe there's another one. I can't think of it offhand. But the spin angular momentum is one quantum mechanical operator that has half integer values. Again, as I'm bloviating right now, just kind of sit tight as if I'm telling you a story, and because all of this you're not going to need to know to do one more problem on your final. But it's all window dressing, like setting the stage for what we're about to do. So yeah, so an object, you're going to find out, like in quantum mechanics, that you can have spin up and spin down. And that, to me, is like dealing with the theta, but you're not dealing with it directly. But, you would think that spin, oh, that's how much it spins, right? Well, you would think so, but it's like, it's a strange little kind of thing. It's more or less orientation. Because you're dealing with the spin by total angular momentum, you're already taking care of the spin values and stuff, but how it rotates. But spin is like orientation, it's axis of rotation, really. And there's particular quantum values with that. There's half and plus 1/2 and minus 1/2. It means it can be up, it could be down. That's basically what that means. Okay, so now we have this electron. It's got spherical polar coordinates, r, theta, and phi. And we're about to transform our x, y, and z into polar coordinates. Spherical polar coordinates. Okay, so we have the radius of the sphere r, and then we have theta here. Now, if we look at just this midpoint, this r here, and theta, we can see that the z-axis is going to be r cosine theta. So the z-axis is here. And so even if we take, alternate interior angles here, so we're going to do theta there, and then theta over here. And then this line would be r cosine, because it's the same line as this guy over here. Okay, so it's a big parallelogram. Okay, r cosine theta. And that's what z means. That's what z becomes in spherical coordinates. Now x. Now we can take start taking a look at what x is going to become by looking at this phi angle. The x-axis is here, so we know that that's going to be say that's going to be cosine of phi. Okay. And it's also going to be a combination. It's not just going to be cosine phi, but it's going to be a combination of r sine theta and cosine phi. Why is that? If we take this sphere, and if we're looking at this middle green line, all right, and we rotate this, we take this sphere and we'll rotate it back to the x-axis. That means we're going to do a clockwise rotation. Clockwise rotation. Follow the green arrow. Okay, so this line here is r sine theta, right? Because theta is up top, and then this leg is the sine component. So this is going to be r sine theta combined with cosine phi, where phi is here. So that's what x becomes r cosine phi sine theta. So again, if you didn't see that, don't worry about it. Just telling you that that's what x, y, and z are going to become, or so far what what x and z are becoming. So z in terms of spherical coordinates is r cos theta, and x in terms of spherical coordinates is r cosine phi sine theta. Now, likewise, or similarly, the y-axis, if we now rotate it counterclockwise, we're going up to the y-axis, we see that y-axis is a combination of r sine theta. So we're just taking this r sine theta leg and we're either going to map it back to x or map it up to y. And then if we map it up to y, then y is going to be equal to r sine theta sine phi. Y sine phi, okay, remember phi is here. And then alternate interior angles phi is going to be over here. And so in this configuration, the y-axis is the sine of phi. It's opposite phi. So we have now rotated r sine theta onto y, and its y is already r sine phi, so it's going to be r sine theta sine phi. So that's what y is going to be. So those are your x, y, and z axes in terms of spherical polar coordinates. And I've written them again here. And so what we're going to be doing is I'll explain it again, but what we're going to be doing is you're going to derive this equation that I have before you. I'll set it up as much as I can get, basically without, giving you the answer, like giving you everything. All you gotta do is one or two little moves, and you got this derivation. So what you're going to be doing, your last question for your final exam is to derive the LZ operator. LZ phi is equal to IH bar del psi del phi. Okay, so like we did with the Hamiltonian before, H psi equals E psi. Well, it's the same idea. So LZ is an operator, psi is an eigenfunction, IH bar del del phi is an eigenvalue, and psi there. So, and the wave function is going to dictate what kind of eigenvalues we get. And there's going to be a particular integer value that we denote by the letter m, which is going to be the orbital angular momentum quantum numbers. We won't do those, but I just wanted to tell you that this LZ, the angular momentum, the quantum mechanical version of angular momentum, produces a series of possible solutions dictated by the angular or by the orbital quantum number m, because n was already taken for energy, right? So, and then we have another, so I'll just put it this way. M quantum number relates to the rotation axis phi. L quantum numbers relate to the precession angle theta. And N, well, that's really what the energy is like, it's like with numbers, scalars like energy. Because you take quantum mechanics, you're going to see eigenfunctions called Legendre polynomials and associated Legendre polynomials. Regular Legendre polynomials deal with the precession of the electron, how it wobbles. The associated Legendre polynomials deal with how it rotates, which is phi, right? And it's pretty much it. And then, there is a part of that whole complex the spherical coordinate system that deals with radius, but only going to get one radius. The sphere doesn't change shape, so but you can get different precessions and different rotations. So that's what we have. Okay. So now let's take this LZ. So let's deal up. Keep wanting to use my finger. So we're going to transform LZ psi into its eigenvalue function form. Okay, so LZ psi is equal to negative IH bar X del psi del Z. Now, why do we get that? Because we saw that LZ itself, is IH, negative IH bar X del del Y. And so we just put the psi in there to make it psi. Okay, that's all we're doing. It's negative IH bar X del del Z with the psi minus Y del psi del X. Okay, so our next part is we're going to now break everything apart into partial derivatives. And so I want to pause, stop this video, and then continue with the next one and starting to discuss what this is all about. You may have seen this in some form. This might remind you of a particular rule called the chain rule, and we're going to be using that when we dissect our components of our angular momentum operator. So that's going to be our next video.